Hey everyone, and welcome back to the channel. It's part 3 of our deep dive into this awesome Kaggle competition on predicting post-HCT survival. And remember, HCT stands for hematopoietic cell transplantation. If you're just joining us, definitely check out the first 2 videos in this series. We did a thorough exploratory data analysis, EDA, in the first one, and then we studied some cool boosting tree models in the second. You'll find the links down in the description. Today, we're tackling something sophisticated, a pairwise ranking network. I stumbled upon this amazing notebook by Kagler's Albanito and Dreaming Tree. I just had to break it down for you all. Now, I'm learning right along with you. I didn't write this notebook, but I did create the diagrams we'll be looking at, based on my understanding of the code, to help us visualize everything. We're going to explore the code, unpack the key ideas, and hopefully learn some powerful new techniques for survival analysis. The title says it all: Refactoring Pairwise Ranking Network. The main goal is to predict survival time, and the author's using this pairwise ranking approach, which is quite different from the popular tree boosting models for this type of problem. First things first, we gotta get our tools ready. We've got a bunch of pip install commands here. It's all about making sure we have the exact right, compatible versions of everything, especially for things like PyTorch Tabular that we'll be using later. Okay, this section is all about getting the data into shape. The author's written some helpful functions, which is awesome for keeping things organized. getXCat, this is our categorical feature handler. You know, things like gender or disease type, stuff that isn't numbers. It uses label encoding, which basically turns each category into a unique number, like male equals 0, female equals 1. Neural networks love numbers, so this is essential. Preprocessed data. This is the main data prep function, and it's doing a bunch of important stuff. It splits the data into categorical and numerical features. It uses standard scalar on the numerical features. That means scaling them so they have a mean of 0 and a standard deviation of 1. This helps the network train way more effectively. It uses simple imputer to fill in any missing numerical values, using the mean strategy, replacing those missing spots with the average. Get categoricals. This function figures out which columns are categorical and which are numerical, and it also handles some edge cases, like getting rid of categorical columns that are, like, all the same value, which wouldn't be helpful at all. initDL, this one builds those data loaders we just talked about. Notice it takes the categorical data, the numerical data, and the target variables. F's time, that's the survival time, and F's, which tells us if the event actually happened. And check this out, it log transforms F's time. That's a standard move in survival analysis because survival times tend to be skewed. Add features. This is where things get creative. The author is actually making up new features from the existing ones. For example, theirs is cytoscoresame, which checks if 2 related columns have the same value. These engineered features can help the model pick up on patterns it might otherwise miss. Load data, just a simple function to load in our data files, CSVs, and then add those awesome new features we just talked about. All right, now we're getting to the heart of it. This diagram I made shows the architecture of the LitNN neural network, the real brains of this operation. I drew this up to help us understand what's going on, so let's walk through it together. First, on the left, we've got our inputs, our categorical features and our continuous features, all feeding into the network. The categorical features head into these cat embeddings blocks. These are embedding layers, and they're super important. Instead of just saying, like, Category 1, Category 2, each category gets its own little vector of numbers. This lets the network capture much richer, more nuanced relationships between categories. Next, see how those embedded vectors get combined with the continuous features. That's the concatenation step. We're just bringing all our feature information together. Now, this combined data flows into the MLP, or multi-layer perceptron. This is the main part of the network where it learns all those complex patterns in the data. Inside the MLP, we've got this ODST layer. That stands for Oblivious Decision Stacking Trees. It's a special kind of layer based on decision trees, kind of like what we saw in the last video, but with a twist. It's designed to be differentiable, meaning we can train it using gradient descent, just like the rest of the neural network. We'll take a closer look at how that works in just a second. Then we have batch norm and dropout. These are just standard tricks of the trade to help the network train more stably and avoid overfitting. Basically, making sure it doesn't just memorize the training data. The main output is what we're ultimately after, a prediction related to survival. But there's also this auxiliary task. It's like a little side quest for the network. It's another prediction task that provides an extra learning signal, helping the main task learn even better. And now the loss computation. This is super important. The main loss uses this pairwise ranking approach. This is perfect for survival analysis. Instead of trying to predict the exact survival time, the model learns to rank individuals. It's trying to figure out, will person A likely survive longer than person B? And get this, there's also a race loss. The author is specifically trying to make sure the model is fair across different racial groups. It actually gets penalized if it makes biased predictions. I think that's really cool. Finally, for evaluation, we use the concordance index, or C-index. This is a classic way to measure how good a survival model is. It tells us how well the model ranks people in terms of their survival. A C-index of 1 is perfect ranking, and 0.5 is basically like random guessing. Okay, let's zoom in on that ODST layer we just talked about. I made another diagram to show how this part works internally. On the left, we've got an example of an oblivious decision tree. The key thing here is oblivious. It means that all the nodes at the same depth use the same feature and the same threshold to split the data. That's different from a regular decision tree, where each node can pick its own feature and threshold. Now on the right, we have the ODST computation flow, basically the step-by-step process. First, we have our input, a batch of data. Then, feature selection. The model decides which feature it's going to use to split the data at each depth. Next, bin decisions. This is where the magic happens. Instead of hard yes or no splits, we get soft decisions, probabilities. Then, response weights. Each of those leaf nodes at the bottom of the tree has a response, and these responses get weighted based on the probability of reaching that leaf. Finally, the output is just a weighted sum of all those leaf responses. The big takeaway here is that ODST combines the power of decision trees with the flexibility and differentiability of neural networks. It's a really clever way to capture those complex, nonlinear relationships in the data. Then let's check the pairwise ranking. I made another diagram to help us visualize it. Input data, C at the top. We have our patients P1, P2, etc., each with their survival time, Y, and whether the event happened, Fs. Step 1, create all possible pairs. The first thing the model does is create every possible pair of patients, but it only keeps pairs where at least one of them experience the event. Step 2, compare pairs. Now, for each pair, the model compares their survival times. It figures out who should be ranked higher. In the example, P4 should be ranked higher than P1 because P4 lived longer. We represent this with a Y value, -1 if the second person should be ranked higher, and it would be +1, though it's not shown, if the first person should be ranked higher. Step 3, apply mask. This is crucial for survival analysis. We can't always compare everyone directly. There are 2 invalid cases. Invalid case 1. If someone is censored, meaning we don't know their exact survival time because they were still alive at the end of the study or lost to follow up, and they appear to have outlived someone who did experience the event, that's an invalid comparison. Invalid case 2. The opposite, if the person who did experience the event appears to have outlived the censored person. So this mask filters out those invalid comparisons. We only want to learn from valid rankings. Step 4. Calculate hinge loss. Finally, we use a hinge loss. Basically, it penalizes the model if it gets the ranking wrong, and it has this margin that encourages the model to be confidently correct. We average this loss across all the valid pairs. All right, it is time to go through the code. This section is where we define the PyTorch model. We've got 3 main classes here. Cat embeddings. This class handles those categorical feature embeddings, like we talked about. NN. This class takes those embeddings, combines them with the numerical features, and builds that core MLP, including the ODST layer. LitNN. This is the main event. It inherits from PL, LitNN module, that's part of PyTorch Lightning, a framework that makes training way easier. This is where we define that super important loss function. Let's zero in on the calc loss function inside LitNN. This is where the pairwise ranking magic happens. 1. Combinations. First, it generates all possible pairs of data points. 2. Filtering. Then, it keeps only the pairs where at least one person experienced the event, like, sadly, death. 3. Y. It creates this target variable, y it's +1 if the first person in the pair survived longer than the second, and otherwise. 4. NN, functional, relu, y, pred left, pred right plus self. H params, margin. This is a hinge loss. It basically penalizes the model if it gets the ranking wrong, and that margin adds a little extra buffer, making the training more robust. 5. Get mask. Not all pairs are valid due to censoring. This mask function takes into account the censored data. 6. Averaging. Finally, the loss is averaged over all the valid pairs. And don't forget get race losses. That function calculates a separate loss for each racial group to encourage fairness. Okay, time for the main event, training the model. The main function first loads up the data. Then it uses stratified k-fold for cross-validation. This is super important to make sure our model generalizes well and isn't just memorizing the training data. It splits the data based on race group and whether the patient is a newborn, making sure each fold has a good mix. It calls this train final function for each fold. Train final function. It creates an instance of our LitNN model. It uses PyTorch Lightning's trainer to handle all the training loop details. So convenient. We've got callbacks for things like saving the best model checkpoint, keeping an eye on the learning rate monitor, and even using stochastic weight averaging, which can often give us a little performance boost. It trains the model and then tests it out on the validation set. Then after the training loop finishes, the main takes the prediction of each fold model and averages them to create final prediction. Finally, the submission file is generated and ready to upload to Kaggle. Wow, that was a deep dive. We've explored a sophisticated notebook that uses a pairwise ranking network for survival analysis. The cool parts are that pairwise ranking loss, the clever ODST layer, the built-in focus on fairness, and how nicely it's all structured using PyTorch Lightning. I hope this breakdown was helpful and you learned something new. Make sure you check out those first 2 videos in this series if you haven't already. Give this video a thumbs up, subscribe to the channel, and let me know down in the comments if you have any questions or if there are other notebooks you'd like me to explore. Thanks for watching.